Yes.
The station's on top of a building. The state that took out the building should be correct.
It doesn't. It doesn't.
Some of the sections might be.
Yeah, I mean, they took pictures of all the buildings, and then the ones, I mean, the buildings were fine. The ones that, I mean, I was amazed. And in fact, Eric and I had a huge fight when he first went in and put the sites in, because I didn't think putting them on buildings was a very good idea. But he lucked out. Almost all of them stood up. So we're at a stalemate on that argument. But so here you can see this moved this way, that moved that way. This did move quite a bit to the west relative to this side, which is consistent with our left lateral strike slip motion. And then you can see what happens in the far field. And then this just shows you the data from 2004 for a few sites up to present. This shows from the earthquake happened, and then on the top figure, I just have it highlighted here. Here's what the position was before. You can see there was a nice linear trend saying it was just cruising right along, constant velocity, and then after the earthquake, boom. So that shows you the post-seismic displacement. Change in north, change in east, and change in europe for the site LEOG, which is the one that is zooming off to the west. And these are 3 other sites. Shows you what the earthquake did. Okay? There's just the finite fault slip model that was produced by Caltech, and you can see right after the earthquake happened, based on the arrivals of the seismic waves with seismometers all around the world. And then you can see here, for a strike slip fault, all the arrows should be like this, and you can see that they're not. So even the slip distribution shows that that was the case. You don't see that. This just shows it again. It shows the predicted ground motion. And then the next slide is, this is a little bit hard to see. This shows the same 2 things I showed before. This is the same as this. It's just blown up a little bit of what the motions were. Now this is a model that uses the slip distribution calculated from the seismic wave information here to determine what the surface displacement should be at ground level during the earthquake. This just shows you the orientation of the fault, and these are what the velocities would be if we assumed, okay, that we had a fault that looked like this, with a slip distribution like this. This just tells you how consistent the data set is in the analysis between looking at the seismic wave and looking essentially at this ground motion model. And the ideal would be for these vectors here to match these vectors here, and they don't very well. So that tells us that we don't fundamentally understand yet what's happening, and that's what the objective is going to be going forward. What don't we understand, and what was peculiar about this earthquake. And that's it. Oh, sure. In the Caribbean, yeah, along the septentrional fault, there's a town in the Dominican Republic called Santiago, which I would be worried. And then there's San Juan in Puerto Rico also. Puerto Rico doesn't look like the risk is quite as high, but it is. The building codes are not very good in the Caribbean in general. Yeah. What about London? Well, that's a similar sort of thing, right? It's like the prediction we made, and that's what's been happening in Southern California for years, which is we know that the San Andreas is overdue based on historical seismicity, looking at the GPS geography, doing the fault trenching, and so forth. But it hasn't happened. But it will. Yeah.